Hello, it's Keith here, and this is lesson 5 of my so-called ChibiFighter series, in which we look at this little ChibiFighter test game that I made. Now, today we're going to be discussing the animator routines. As the game is playing, obviously the characters will be moving around, and if the computer player decides to keep moving to the left, that decision to move is being done by the AI code. But when things happen, like for example, if I decide to punch, there is a sequence of actions there. The hand will come out, then the hand will come back, and there is also the action of the player being defined with an attacking value and things like that. And if I decide to jump, there is a jumping animation there as well. So basically what we're going to do today is we're going to discuss those animators and how they actually work with regards to the game. The animator code was taken from the ChibiAkumas Ep2 game. That game, in addition to the first game, added an animation scripting engine. I was quite happy with how well it turned out, and so I decided to base the code for today's version on that. Now, the only slight difference is this version is more minimal. It doesn't use all of the functionality. It also is a bit more optimized. I made a few tweaks and improvements to the format of it so that it used a little bit less memory. So that is what we're going to be looking at today. So let's go over to the source code and let's take a look. Okay, so this is the code that actually does the job of the animation. But first of all, let's take a look at the actual data that it uses. Okay, so how does the animations work? Well, there are a couple of rules with regards to the animators. The players can have a total of 15 different kinds of animator, and that's because animator 0 is nothing, no animation, just a static image. And each of these animations can have a total of 16 different stages within that animation. Now, each stage could be something like a change of the sprite, a move of the direction, and so on. There can also be internal loops within an animator. So the first 3 stages of the animator could loop a few times and then it could continue. The animation can also spread over different periods of time. So one animator could update the frame of the sprite every single tick of the game. Another one could work every other tick, every 4 ticks, every 8 ticks, and so on. And so there is a lot of complexity, and even things like with regards to the limitations of 16 different stages of the animation, you can actually chain animators together and things. So there is a lot of capability there within a very simple piece of code. Now, why is it that there's only 16 possible animators, with animator 0 being unused, and 16 frames of animation? Well, this is because the animator uses a single byte. The animator's byte is split into 2 nibbles. One nibble is the animator number and one nibble is the frame number, and that's where those limitations come in. Now, this is the lookup table of the animators for one of the characters here. So this Chibico walk would be animator 1, this would be animator 2, this punch, kick, and so on. So we've got a variety of animators, and then here is the actual animation script itself. Now, the first byte of the animation script is basically a mask, and this is ANDed with the current tick of the game. Now, at every frame of the game that's drawn, the game tick goes up by 1, and so this is a number that loops around, goes from 0 to 255 back to 0, and so on. Basically what we do is we AND that with the current mask here, and that will define whether this animator is to proceed for this frame of the game. So basically a mask of 1 here is a very fast animation, a mask of 111 here is a much slower one, and so we can control the speed with which the animation occurs here. Now, every following command from that, whatever the command, will have a total of 4 bytes. The first one is the command type, so animation sprite here, and the following 3 bytes, the function of those will depend on the actual command that was executed. Now, we have some definitions for the animators here. So 0 is the empty. This does nothing, effectively meaning that frame of the script does nothing. Sprite would change the sprite, and then we have 3 following bytes to that, and we're calling them X, Y, and Z here. And we've got a brief description of what each of them do here for each of the possible animation types. Animation halt is the end of a script, and that will effectively reset the animator number to 0, ending the animation. So that's not a loop. We do have a loop command for looping animations. You can see that with the walk. The walk will go on forever until the animation is changed by the fact that the player or the computer has released the direction of movement. So that is the difference between a halt and a loop. So how do we actually process the animator byte? Well, we use this object animator function here. Now this will be passed a single byte in the accumulator, and this is the combined animator number and frame. As I say, a single byte of the sprite definition, the player definition, it defines the animator, and so we will take that in the accumulator. Now we're disabling interrupts here if needed. Do DI will be a macro that's defined to either DI or nothing, depending on whether our interrupt handler needs the shadow registers. We use the shadow registers during the object animator routine, and so the ChibiTracks music tracker I've written doesn't need shadow registers, so we don't need to disable interrupts for that. But if you were using Arcos tracker, or if you were using a firmware one that did, you would want do DI to actually be a DI command, but otherwise it can just be nothing. So what we're doing first is we're running get animator mempos. Now let's take a look at that. Well, here it is. Now what we're going to do is we're going to take the byte in the accumulator, which is split into two nibbles. The bottom nibble is the animator number, the A bits there. The top nibble is the tick, the line of the script that we're currently running. So what we're doing here is we're getting the bottom nibble here, and we're effectively multiplying it by 2 here. We are subtracting 1 here with that dec A because animator 0 doesn't exist in our lookup table. It's no animation, we just do nothing in that case. And so what we're doing here is we're effectively selecting one of our animators within this list here. So Chibico Walk is animator 1, Chibico Punch is animator 2, and this get animator mempos is selecting one of those animators. So that is what we are doing here. Now what we're then going to do next is we are going to get the timer ticks occurred, which is the game tick, and we're going to AND that with the mask of the first byte of the animator script. Now if this is a non-zero value, then we are going to do nothing and we're just going to return. Now when we ran get animator mempos, we loaded the B register with the old animator value, and so we're restoring that here. Now you will remember maybe that at the start of our animators we had this byte here, which is a mask, and if the result of ANDing that with our current frame number is 0, then we're going to update, otherwise we're not. And so the larger the value in there, the more bits that are 1, the less often that we will update the frame of animation. Now if we're going to update the frame of animation, what we're doing is we're skipping that byte mask there, and then what we're doing here is we're getting the top nibble of the animator number, which is the tick of the animator, effectively the line of the script that we want to run this time. Now each line in the script is 4 bytes, so we're shifting that to the right by 2 bits, effectively multiplying that top nibble by 4, and we're then shifting to the position of the current line of the script. We're then loading in the byte, which is the command number, and we're then going to use this vector array to select one of the commands. Now this vector array here has an address of each of the possible commands, and basically what we're going to do is we're going to jump to one of those commands. We have a special command to do this called vector jump push HL first. You see, we don't want to lose the true value in HL, so we're pushing the value in HL here. We're then loading the address of the vector array, and we're going to use this vector lookup command to select one of the addresses in that vector array by basically doubling the accumulator and then adding that to H and L and loading the address in that vector array into HL. So this has selected the value in the accumulator as an offset multiplied by 2 to the vector array that was in HL, and we're then going to do exsp kind of HL. This is effectively swapping the value on the top of the stack, which is the HL we pushed just here, and it's swapping that with the new HL, which is now the address that we're going to jump to. And so when we return here, what we've effectively done is we've jumped to one of the addresses in the vector lookup offset by the accumulator, and we've kept the old value in HL, which was the sequence of bytes that is our command script. A bit tricky there, I know, but so basically what we're going to do is we're going to have a sequence of possible options now that are going to do tasks for us. And so let's take a look at some of them. For example, here is the sprite command. This is one of our possible scripted commands, and this is now going to read in a sequence of bytes from the HL commands now. Basically, if we have a look at one of our commands here, here is a sprite example. This is the sprite command here, and the first byte there is a 2. Now that is going to be the sprite number, and so you can see here what we're doing here is we're loading in the value from HL, and we are setting that as the sprite number of IX, and when this animator command is executed, IX will point to the player that we're trying to animate, and so this is updating that player's sprite number. We're then loading in the sprite refresh byte here, and we're ORing that with the next byte in our sequence. And what this can do is this is allowing us to force a refresh of the background. The min tile code that I wrote, it's a bit buggy with regards to half tile shifts. It's really designed for full 8 pixel jumps because it's basically using the same code for the tile map as the sprites. The sprite code isn't that good. It's called min tile because it's very simplistic, and so this is a workaround to allow a full refresh of the background for sprites that are prone to glitches, shall we say. So that's what that is doing. And then the final one here, the third byte in the sequence, is allowing us to flip around the player's sprite. Now the min tile can do an X flip of a sprite, and so basically if the third byte in the sequence is 0, we're leaving the current direction as it is, but if it's a 1 or a 2, we are forcing the flags of the sprite to be a direction, either a 0 for right or 1 for left. So that's what we're doing with the third byte in the sequence. When we've done our command, our animator, we always run object animator update. Now if we just find that, we'll see that what it basically does is it simply increases the tick. Now what this does is we're basically just adding 1 to the top nibble of our original value, and then we're returning that value in the accumulator. And so the calling routine will save this animator data into whatever the parameter it was using was, and it will then use that new updated version next time. And so, as I say, the bottom nibble is basically the animator number, and the top nibble is basically the tick, the line of the script. So that is the one for updating the sprite. We do have a variety of other functions though. We have the move function. This will move the sprite by an XYZ amount. Now X is across the screen, Y is up and down, as in jumping, and Z is in and out of the screen. Now the game itself has a it's kind of simulating the Renegade type of the Teenage Mutant Ninja Turtles game type, where you can move up and down a virtual floor, if you will, within the game, and that's what the Z axis is. Now I'm using 16-bit values for X, Y, and Z for flexibility, although we're actually only updating the top byte here in 8 bits here, but there was a certain amount of future-proofing in this code. It's more of a tech demo than a real game. I was sort of playing with the thoughts of, well, you know, I could create a Street Fighter 2 type game, or I could create a Ninja Turtles type of game, which is a game I far prefer to Street Fighter 2. So I was playing with various things, and I was trying to add some future-proofing, and I was using 16-bit values for the X, Y, and Z here. So this is basically taking the first parameter and using it as the X offset. Now this do flip IX here, this is taking into account the direction the character is facing. Now this is used for when the player is hurt, the player will be knocked back, but the direction the player should be knocked back depends on the direction the player is facing. And so if the player is facing the opposite direction, we are flipping the x-axis here, and so that's what that's doing. No such need for the y-axis, the second byte, and the third byte is the z-axis, and so that is the move option. We also have the attack option. This sets the attack of the current player. Now a positive attack is like a punch or a kick, so it's an amount of harm that can be done to the enemy. A negative attack is actually defense, so an attack of -1 is if the player is blocking, things like that. So that's what that's for. More interestingly, we have the spawn command. Now this one's a bit of a complex one. Basically, when the player wants to protrude a fireball, we actually have that as an animator, and so the animator command is spawn object. The first and second parameter bytes are the address of a script, an extra add-on set of parameters, and the third byte is unused there. And the script here is literally a set of bytes here, which are parameters which are passed to the sub-object. So let's see what happens. So basically, the first thing we're doing here is we're getting the address of the sub-object of the player. Now this is a second sprite object that the player can employ. And so we're loading that into IY. Then what we're doing is we're getting the address of that set of definitions there into HL. We're loading first the low byte from HL. We're then loading H from HL, losing the original HL, and we're loading that into the high byte, and then we're loading L byte from A. So HL now points to that set of parameters. And then what we're doing is we're loading each of the parameters into the respective parameters for the sub-object in IY here. And so you can see all of these here. We are loading these in basically from this set of parameters here. And you can see I was playing around with setting the sprite and the attack here as well, but I decided that wasn't necessary. So it's remmed out in the code here, but you can see how you could turn it on and add other functionality if you needed. Now, as well as what we've discussed there, you'll see that other things like condition loops. These are designed for animators that do a small repeating action and then an occasional action. So basically maybe you could have 2 frames of walking and then a jump every 16 frames or something. And this can be done with conditional loops. The condition is based on the ticks occurred, not used within this game. And we also have conditional jumps as well, again, something that wasn't used in this game. Calls to subroutines, so we can have part of our animator call a subprogram. I could have actually used that instead of writing this spawn command, I guess. Yeah, that would certainly be another option there. Just depends what you feel most appropriate. But I mean, basically, as I say, this program, this animation script program was designed for the ChibiAkumas Ep2. It worked extremely well. Very simple piece of code, but with a lot of power. It gave me lots of weird and wonderful enemies in that game, and so when I decided I needed something similar for this game, I re-employed it for this, and I still have no complaints, so I'm sure I will use it again in future games. Anyway, as I always say, you're welcome to go to my website, download the scripts for today's example, the source code and all that kind of stuff, and you're welcome to use anything you found in it, in anything of your own, and you don't need to give me credit. And by all means, if you find what you've seen today a little bit confusing, take any of the ideas from it. It's often best to just write your own stuff, and just if you heard something today that made sense to you and you heard something else that didn't, take the ideas that made sense to you and start from scratch with something simpler that does what you want, or something better that does what you want. As I say, I'm never trying to say that what I'm doing is the best. It's just what I've come up with that worked for me. Anyway, I hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.